Hello, everybody. In the previous class, we have derived Poisson-Boltzmann's equation, which is Poisson's equation relating the second derivative of the electric potential to the local value of the electric charge density. D2 phi by dx squared is negative rho of x charge density divided by epsilon naught epsilon. So this is Poisson's equation. Poisson-Boltzmann's equation relates the charge density to the concentration of electrons and holes, as well as the concentration of ionized donors and acceptors, which are expressed, concentrations of electrons and holes are expressed in terms of the electric potential using Boltzmann's approximation. So that's Poisson-Boltzmann equation. And I also promised that Poisson-Boltzmann's equation is solvable in spite of its slightly intimidating look. But I will do this not in this lecture, I will do this in the next lecture. In this lecture, I would like to introduce two useful approximate approaches to Poisson-Boltzmann's equation. One is due to Peter Debye, and the other is due to William Shockley. So both, by the way, both Debye and Shockley are Nobel Prize winners. Peter Debye has made so many contributions, fundamental contributions to such a diverse range of research areas that at this point, I'm not sure what he got his Nobel Prize for. I believe he got, yes, of course, he got his Nobel Prize for the theory of X-ray scattering and for the development of an important X-ray scattering technique, Debye-Scherrer method. But Peter Debye contributed to thermodynamics, the theory of specific heat of solids, to the theory of electrolytes, and his contribution to the theory of electrolytes, the so-called Debye-Huckel theory that he developed together with Erich Huckel, is directly transferable to semiconductors, and it will be discussed today in this lecture. Now, William Shockley is also a great physicist. He made foundational discoveries in the theory and experiment in semiconductor physics. So probably today is the time that you are introduced to one of his most important, one of his many important contributions, I should say, the depletion approximation. All right. So let's go. Here is the Poisson-Boltzmann's equation, which we write down assuming complete ionization of impurities. So instead of the concentrations of ionized donors and acceptors, I just write down donor and acceptor concentrations, assuming that all of the impurities are ionized. In practice, it is 99.9 or so % ionized, but all right. Within Boltzmann's approximation, we can write down the concentration of charge carriers, electrons, and holes related to their bulk values far away from the surface. Yeah, I should introduce the setup first. So here is our semiconductor slab. It is thick. Yeah. Its surface is maintained at the electric potential phi surface, and far away from the surface, the potential is assumed to be zero. And also, of course, the electric field is zero. It goes to zero pretty quickly as you move away from the surface. And the question is, how quickly does it go to zero? So, all right. So with Boltzmann's approximation, we can write down the concentrations of mobile charge carriers, electrons, and holes, like so. N naught B and P naught B are the electron and hole equilibrium concentrations in the bulk of the material that is far away from the surface, where the potential goes to zero. Electrons are negatively charged particles, so they are attracted to the regions where the electric potential is more positive, hence exponential is raised to the power plus pi of x divided by the thermal voltage V thermal at room temperatures. So thermal voltage is the ratio of the thermal energy to the elementary charge, and the room temperature's thermal voltage is 26 millivolts. So if you express thermal energy in electron volts, you just drop the word electron to get the voltage. So 26 milli electron volts is the thermal energy at 300 kelvins, and 26 millivolts is the thermal voltage at 300 kelvins. Now for holes. Holes are positively charged particles. They are attracted to the regions where the electric potential is more negative, right? Because positive and negative attract each other. So hence we have minus sign in the exponential. So if phi of x is negative, then negative phi of x is positive. By approximation, or the Debye approximation, is valid when the value of the surface potential is weak. It is smaller than the thermal voltage. In which case, you can linearize these exponential factors using the well-known method of linearizing functions in general. So let's say if you have a function f of x, and you want to linearize it, approximate it with a linear function, let's say at small values of x, then you aim at correct reproduction of the value of the function at x equals 0 and the first derivative of the function at x equals 0. So you linearize f of x as f of 0 plus f prime of 0, the first derivative, df by dx at x equals 0 times x. Plus there will be higher order terms like 1/2 d2f by dx squared at x equals 0 times x squared plus 1/6 and so forth. But we keep just the first order term. The first derivative of an, so now if you wish to linearize an exponential function e to the x, the value of the exponential at x equals 0 is 1. The value of the first derivative of an exponential function at x equals 0 is also 1. E to the power 0 is 1. So hence the linearized version of the exponential to the power either plus or minus phi of x over v thermal is 1 plus or minus phi of x over v thermal. So that's our linearized exponential. And now we plug in the charge carrier mobile electron and hole concentrations with the exponentials linearized like so into the Poisson-Boltzmann equation. So these are our carrier concentrations. And we plug in these charge carrier concentrations into the Poisson-Boltzmann equation. Then this is what we have. I have separated the terms in the electron and hole concentrations. I have separated the fixed terms, N naught bulk and P naught bulk, from the terms which are proportional to the electric potential phi of x. Okay, so this is P naught bulk, P naught minus N naught of x, the last four terms, 1, 2, 3, 4. And using the charge neutrality condition, of course, the whole structure is electrically neutral far away from the surface. Near the surface, it may have a little bit of charge, but far away from the surface, the semiconductor is electrically neutral, which means that the sum of positive charges, holes, and ionized donors must be balanced by the sum of negative charges, electrons, and ionized acceptors. So ionized donors and holes. Donors are completely ionized, acceptors are completely ionized. And now, using the charge neutrality condition, we notice that the first four terms in the linearized charge density nicely and beautifully cancel out. So this is what I have for my linear charge density. It only linearized, not linear, linearized charge density. It only depends on the electric potential. It is proportional to the electric potential phi of x. All right. So plugging in this linearized charge density into the Poisson's equation, Poisson-Boltzmann, we have the linearized version of thereof. Notice that there is a plus sign in front of in the right-hand side, because in the original version of the Poisson's-Boltzmann equation, where is it? Here we had a minus sign, but then we have linearized P naught of x and N naught of x, which turned out to be negative as well. Negative phi of x over V thermal times, yeah, like this. So this minus and this minus mutually canceled. We got a plus. So the second derivative of the potential is potential multiplied with some factor, with some number. And that number, like dimensionally, even dimensionally, this number has the dimension of inverse distance squared, because you have potential. The dimension of the left-hand side is volts per, let's say, squared centimeter. So the dimension of the right-hand side must also be volts divided by squared centimeter. So this parameter, which is measured in squared centimeters or squared nanometers or whatever, something meters squared, is the square of the Debye length. So we introduce this, take the square root, you get the Debye length squared. You get the Debye length. So square root of epsilon naught epsilon, the electric constant, times the thermal voltage, divided by the elementary charge, times the sum of the bulk values of equilibrium electron and hole concentrations. So our Poisson-Boltzmann equation is written as follows. The second derivative of the electric potential is electric potential divided by Debye screening length squared. And the solution of this equation is simple. It is just an exponential function, because exponential function is the only function that is not afraid of differentiation. So, or more generally, exponential to the power ax, its first derivative is a times e to the power ax, second derivative is a squared times e to the power ax, where a can be either positive or negative. So in this case, the argument of the exponential must be negative. More generally, we could have written down the term which contains exponential to the power plus x over lambda Debye lambda d, but this term blows up to infinity as you go away from the surface, and we know that the electric potential must go to zero as you go away from the surface. So the term with the positive argument in the exponential is unphysical. It does not. It does not agree with the boundary conditions. So, all right, so the surface potential at x equals 0 has the value phi surface. This is correct boundary condition, right? And the second derivative of this function is indeed this function itself divided by lambda Debye squared, which is the right-hand side of the linearized version of the Poisson-Boltzmann equation. So, all right, so that's one useful solution, which is valid when the surface potential is small. I would like to point out that the Debye screening length is inversely proportional to the square root of the total charge carriers concentration, which is the sum of electron concentration and hole concentration. So the sign of the charge carriers does not play a role here. You just add them up. The typical values of the Debye screening length, let's say for thermal voltage of 26 millivolts, it depends, of course, on the charge carrier concentrations in the bulk of the material. And the higher the carrier density in the bulk, the smaller the Debye screening length. That is, the faster the electric potential decays to zero, because at high total concentration of charge carriers, electrons and holes, the screening of the surface potential becomes more efficient as you increase the concentration of electrons and holes. And this is, by the way, the reason why. So in semiconductors, the Debye screening length is dependent on the concentration of electrons and holes, ranges from somewhere like 10 nanometers to a few micrometers, or maybe 10 micrometers. So it's about 2 orders of magnitude. In metals, the concentration of electrons is much higher than in typical semiconductors. So in metals, you can have like 10 to the power 23 electrons per cubic centimeter, and the Debye screening length is extremely small. So the screen could be like maybe of the order of an angstrom, or maybe even smaller. So anyway, you cannot use in metals, the Debye screening approximation needs to be used with some caution, and probably a better approximation would be based on Thomas Fermi theory. But okay, I'm digressing here. All right. So in semiconductor, so the take-home message for now is that the higher the carrier concentration in the bulk, the shorter the Debye screening length. And typically, its value ranges between a few nanometers to a few micrometers, something like that. Okay, now let's move on to the next useful approximate formula for the electric potential. It is based on the depletion approximation invented by William Shockley. Let us assume that the surface potential is not too big, not too small. By that, I mean the following. So I mean that it is not too big to convert the minority carriers into the majority carriers near the surface. So let's say your semiconductor is of p-type and the surface potential is positive. This surface potential pushes away the majority electrons away from the surface, and it attracts the minority electrons to the surface. So near the surface, the concentration of electrons is bigger than in the bulk of the material, and the concentration of holes is smaller than in the bulk of the material. So depletion approximation is valid, or generally depletion approximation is valid when the sign of the surface potential is the same as the sign of your majority carriers. So if your semiconductor is of n-type, you can apply depletion approximation for negative values of the surface potential. If your semiconductor is of p-type, you apply depletion approximation for positive values of the surface potential. Okay, now, depletion approximation is valid when the surface potential in magnitude is not too big and not too small. By not too big, I mean that it is not big enough to make the concentration of minority electrons near the surface comparable to the concentration of holes in the bulk of the material. And by not too small, I mean that the concentration of majority holes in the material near the surface is small compared to the concentration of majority holes in the bulk. So you have very few electrons and very few holes near the surface. Now, numerically, these two conditions, not too big, not too small, can be expressed by these two inequalities. So the concentration of holes near the surface, within Boltzmann's approximation, it is the concentration of holes in the bulk, which is the acceptor concentration, assuming that all acceptor impurities are ionized, multiplied with exponential to the power negative surface potential divided by the thermal voltage. And it must be much smaller than the concentration of holes in the bulk. So this means that the surface potential must exceed the thermal voltage by at least a factor of 2.3. Why? Because exponential to the power negative 2.3 is 0.1. approximately. And whenever you have two numbers that differ by at least 10 times, then you can neglect the smaller number relative, usually you can neglect the smaller number relative to the bigger number. So this is what we mean by not too small. Surface potential must be bigger than the thermal voltage by at least 2.3 times, natural logarithm of 10 times. And by not too big, I mean that, all right, so I mean the following. Electron concentration at the surface at x equals 0 is electron concentration in the bulk, which is given by mass action law. So electron concentration in the bulk, electron concentration times the whole concentration equals intrinsic concentration squared. So the concentration of electrons in the bulk is intrinsic concentration squared divided by the whole concentration in the bulk, which is acceptor concentration. So n intrinsic squared over n acceptor is the concentration of electrons in the bulk of the material. Now, to get the surface value of the electron concentration, you multiply this with exponential to the power surface potential divided by the thermal voltage. And by the way, notice that the mass action law also holds for the surface concentrations of holes and electrons. The product of P naught surface times N naught surface is still n intrinsic squared, because n acceptor and n acceptor mutually cancel in the numerator and in the denominator, and these two exponentials mutually cancel. All right, so the surface concentration of electrons must be much smaller than the concentration of acceptors, which is the concentration of holes in the bulk of the material far away from the surface. And this is possible when this implies that the surface potential must be smaller than the so-called threshold surface potential, phi threshold, minus 2.3 thermal voltage, where the threshold potential is defined by this expression, right? If you substitute instead of phi surface this threshold potential, you will find that the exponential assumes the value of n acceptor squared divided by n intrinsic squared. Right? This exponential becomes n acceptor squared divided by n intrinsic squared, and at the threshold surface potential, the surface concentration of electrons becomes exactly equal the acceptor dopant concentration. And if you increase the surface potential above the threshold value, the concentration of electrons at the surface will become bigger than the concentration of holes in the bulk. So the conductivity inversion happens. The minority electrons at the surface becomes majority carriers, and majority holes in the holes which are majority carriers in the bulk become minority carriers at the surface. This is called the conductivity inversion. It is an important effect that will be discussed in the next lecture. Okay, you have received an introduction to this conductivity inversion, what this means. Now, so if this depletion, if these conditions hold, the surface potential is not too big and not too small, then the electron and hole concentrations near the surface are both much smaller than the acceptor concentration. Acceptor concentration is not affected by the potential, by the surface potential. So you have those ionized acceptors both in the bulk and in the surface, and of course we assume that the semiconductor is doped uniformly. But if the total charge density consists of three contributions: negatively charged acceptors, negatively charged electrons, positively charged holes. And they are added up in the Poisson-Boltzmann equation. If acceptor concentration exceeds both electron and hole concentrations by at least 10 times, you can neglect electrons and holes. And you can approximate your concentration of charge carriers near the surface with negative elementary charge. This is the charge of a simply ionized acceptor ion, acceptor atom, times the concentration of acceptors. So this is your surface charge density. And then Poisson-Boltzmann's equation close to the surface assumes a very simple form. The second derivative of the electric potential is a constant. Okay. And the constant is the ratio of the elementary charge times the acceptor concentration divided by the dielectric constant of the material, epsilon naught epsilon. And of course, this approximation is not valid everywhere, right? Eventually, as you move away from the surface, eventually your electron concentration will decrease, your hole concentration will increase, and at some distance from the surface, the assumption that there are not many electrons and not many holes as compared to the acceptor concentration will become invalid. Far away from the surface, the hole concentration is more or less the same as the acceptor concentration. So this simple formula, this simple version of the Poisson-Boltzmann's equation, the second derivative of the potential is a constant, is valid only within some layer, which is called the depletion layer. Inside the depletion layer is called so because the material is depleted of the mobile charge carriers of electrons and holes. The width W of the depletion layer is yet to be found. We do not know it, but this expression is valid within this depletion layer of unknown width W. So here is the physical picture that we have in mind. The potential inside the depletion layer is approximated. The equation that governs the potential inside the depletion layer is approximately this. The second derivative of the electric potential is a constant. The boundary conditions are that on the surface, the potential has a value phi s, and inside the depletion layer, the potential decreases somehow until it reaches the value 0. So the potential at x equals w, the unknown width of the depletion layer, is 0. And of course, at x bigger than w, the potential remains 0. As the width of the depletion layer is where the surface region ends and the bulk region begins. Also, at x equals w, at the boundary of the depletion layer, at the right boundary of the depletion layer, as well as in the rest of the semiconductor, the electric field must be 0. Now, the electric field is the derivative of the electric potential with respect to the coordinate x with the minus sign. E equals negative d phi by dx. So we have another boundary condition, d phi by dx at x equals w must be 0. Okay, now we can solve this Poisson's equation within the depletion approximation. And here is the solution. If the second derivative of a function is a constant, then this function must be a parabola, must be a quadratic function of its argument x. So it is a quadratic function. And here is this solution. This is this function. I have constructed this function so as to automatically satisfy all the boundary conditions. So if you substitute x equals 0, then phi of 0 equals phi surface. The surface potential is phi surface. If you plug in x equals w, then the potential reaches the value 0. You're at the minimum of the parabola when x equals w. And the derivative, of course, at x equals w, the derivative of the potential is also 0. And this quadratic parabolic function is valid only within the depletion layer between 0 and w. Outside of the depletion layer, when x is greater than w, the potential is 0. So this is how the potential behaves. Oh, by the way, the first plot is the assumed or simplified electric charge density adopted within the depletion approximation. So the true charge density somehow decreases. It looks like something like a box. So you approximate this decreasing function with the box distribution. So that's the point. So this is how the electric potential decreases. How do we find the width of the depletion layer? Well, you take the second derivative of phi of x with respect to x obtained using the depletion approximation and substitute the second derivative d2 phi by dx squared, which would be what? Which would be 2 phi surface over w. Yeah, that's the second derivative into the over w squared. So 2 phi surface over w squared is the second derivative of this thing, right? You substitute this into the Poisson's equation, and this gives you 2 phi surface over w squared is E n acceptor over epsilon naught epsilon. So you can find the depletion region width. You can solve it for the depletion region width w, and this is what you get. So notice that again we have inverse square root dependence of the depletion region width on the concentration of charge carriers, and depending on the surface potential. So it also, the depletion region width also depends on the surface, on the value of the surface potential. Unlike Debye width, in the Debye width formula, lambda Debye, we had a thermal voltage in the numerator. So no, let's compare the two formulas. Here is the Debye formula. So let's forget about the factor of 2, which enters the depletion region width, but in Debye's formula, you have thermal voltage in the numerator under the square root, and in the depletion region width, you have surface potential under the square root. Also, the range of the depletion region width is typically the same as for the Debye width. So from, let's say, 10 nanometers to something like 10 micrometers. And it depends on the acceptor concentration. All right. So now that we have the electric potential, we can take the derivative of the electric potential with the minus sign, d phi by dx, and this will give us the electric field. And we see that the electric field decreases linearly from the maximal value at the surface, which is twice the surface potential divided by the depletion region width, given by this formula, to 0 when x reaches, the coordinate x reaches the width of the depletion region. So that's that for today. In the next class, we will discuss the exact solution of the Poisson-Boltzmann's equation. But for now, thank you all very much for your kind attention, and I'll see you next time.